In this lecture, we are going to go over some basic principles of control systems, look at some examples where control system theory can be applied, and define what a control system is and what the limitations of our linear control systems are. Let's get started by looking at some interesting applications of control systems. Here we have this Boston Dynamics robot, and as we can see, this robot has very impressive capabilities. It can jump from one place to another, and perform a variety of tasks. How can this robot maintain equilibrium and also do those tasks at the same time? We can't see it here, but internally, the actuators that give motion to this robot are constantly making adjustments such that the robot can maintain its balance. As the robot moves from one point to another, there is also an internal process that controls the speed of each joint or the torque applied by each joint in the robot. Now, in order to give a command to the robot to apply a certain torque or velocity to joints, we need to understand exactly how the robot will respond to this command. And to this end, we need a solid mathematical modeling of the robot. That's the first step in any control system. Here we have another example of autonomous cars. Certain cars are able to drive fully autonomously. The car has a desired path to go on and also a desired speed to follow along that path. How does the car follow the path and the speed? Again, in order to make the car follow the path and speed, we need a solid understanding of how the car responds to certain commands, such as an angle in the steering wheel or an angle on the throttle, and then you need to implement a certain logic that measures the current speed of the car and the desired speed and takes adjustments based on the difference between them. And the same can be said for the path that the car follows. Another common application of control systems is in quadcopters. We see here that not only the quadcopter can maintain its height and orientation, but also by putting this stick on top of it, we can implement a logic that will make this stick balance. How is that happening? Again, we need a mathematical model that describes the behavior of the stick and the quadcopter when the speed of the motors change. By now measuring the position of the stick through a camera, we can make small adjustments by controlling the position and orientation of the drone such that the stick is always balanced. Along the same lines, here is another type of actuator that is able to balance itself. This system has reaction wheels inside, and again through a mathematical model, we can make it balance on one corner by transferring the impulse that builds up on the wheels to the cube. Even when we apply some external disturbances to the system, we see that it can still maintain its balance. This is only possible if we have a solid understanding of how the system responds to certain commands, such as the acceleration of this reaction. Robotic surgery or robot control is also a very common application of control systems. Consider this example here. We have a surgeon controlling a medical robot through a joystick. The robot now needs to follow the position of the joystick while operating on the patient. The robot is simply replicating what the surgeon does with the joystick. And in order to do that, once again, we need to understand how the robot responds when a certain voltage is applied to a specific joint. Once we know that, we can now create a logic that will tell us what voltage needs to be applied to a joint if you need the robot to move from position A to position B. There are many other applications of control systems. Can you think about any? One example is automatic assembly lines that you've probably seen before. All these robots are controlled either through a position or speed control. Space technology and satellite control are also prominent examples of control systems where a certain trajectory needs to be maintained. Power systems are often regulated using control systems as well. Consider a power station that needs to deliver a certain power to the grid with a certain power factor, or even making sure that the voltage that comes out of the plant is constant. That is often regulated using an internal control system. Smart transportation systems, such as the autonomous car that we discussed earlier, is another application of control systems. At a home, when you turn on or off the furnace, there is a control system regulating the house temperature. When the temperature drops below a certain threshold, the furnace turns on, and when it exceeds a certain value, it turns off. That is regulated by a control system. These are only a few applications amongst many others. What is control engineering? As we discussed before, the first step to control a system that hereafter we can call a process or a plant is to understand the relationship between the input and the output of that process. In the case of the robot, we are giving each actuator a voltage, and you're interested in how the actuator responds to that voltage, either in terms of speed, position, or torque. To understand that relation, we need a mathematical model that describes the behavior of that process. Once we have the understanding of the process, we can now develop a controller to make the process change from one state to another. In the case of the robot arm, the actuator is the motor attached to each joint. Now the controller has all the information about the process and the actuator, and you can now have an inverse mathematical model of the process in the controller that gives what needs to be applied to the motor in order to give a certain position or certain speed. This control architecture is called the open loop control. We trust the model we have, and we assume that based on the model we can determine what actions need to be applied in order to make the system behave the way we want. The limitation of this control strategy is that the model needs to be perfect. It needs to represent the true dynamics of the system, and any external disturbances applied to that system will invalidate this assumption. Think about the car, for instance. If you have a model that describes how the speed of the car changes with respect to the throttle angle, that model cannot account for other conditions such as a road condition or friction between the wheels and the road. The model only accounts for the model of the process. It does not account for external disturbances acting on that process. Open loop control thus only works if the model is perfect and the process we want to control is not subjected to external disturbances that cannot be predicted. Now, what if those disturbances are present? In that case, we use a closed loop control, often called error-based control. The idea is different. You notice here the same structure as in an open loop controller. We have a controller, an actuator, and the process. But now, instead of trusting the model, we are going to measure the output of the system, say the speed of the car that we want to control or the position of the car, using a sensor. And here comes the main idea in control systems. The idea is to now compare the current state or the current output of the system with the desired output. In the case of the car, again, the desired response would be a desired speed, and the output would be the current speed of the car. We now compare them and we create an error function. The controller now takes actions based on the error, based on how far we are from the desired output. This is different from what we had before. In an open loop control, we would use an inverse model of the process to determine what the input needs to be. Here, the control actions are based on the error, not on the absolute value of the input or the output. It's based on how far we are from a desired state. The block diagram that we just saw was incomplete. There are other factors to consider. The first is the disturbance that we discussed before. A disturbance is an external element that acts on the system, which cannot be accounted for. In the case of speed control of a car, the model cannot account for a road slope, for instance. That is an external element to the car. The model cannot account for air drag or weather conditions. Those will affect the relation between the throttle and the speed of the car. Those are external elements to the process, and we call them disturbances. They do have an effect on the output, but now because we are actively comparing the output and the desired output, our controller will automatically adjust the control strategy to minimize the effect of disturbances. Another thing to be aware of is that by measuring the output of our system, we are introducing noise to the system. Now let's look at a simple feedback system to make these concepts a bit more clear. In this example, a control system is implemented to regulate the temperature in a house. The house is the plant we want to control. The input is the heat that is given to the house, and the output is the temperature. What provides heat to the house is the furnace. The furnace is the actuator. And what regulates the furnace, that turns it on and off based on the temperature, is the thermostat, and that's the controller. The disturbance applied to this plant is the heat loss. Heat loss is a disturbance because it depends on many external factors, such as the outside temperature, whether or not all doors and windows are closed. And these elements are very hard to predict. They cannot be included in the plant model. Because of this disturbance, clearly an open loop controller would not be sufficient to regulate the temperature properly. Even if we knew for how long the furnace had to be on to make the temperature change by a certain amount, that would only hold provided that there are no disturbances applied to it, provided that there is no heat loss. The heat loss can change, and therefore an open loop control strategy would not work. Instead, we can consider a closed-loop system where the temperature is measured using a temperature sensor. The measured temperature is now compared with the desired temperature, and that creates a temperature error. Now the thermostat will regulate the furnace, will turn the furnace on and off based on that error. This is very simple to understand. If the error is positive, that means that the desired house temperature is greater than the measured temperature. If the temperature is greater than the desired temperature, the furnace is turned off. If the error is negative, that is, the desired temperature is lower than the current temperature, then the thermostat now needs to turn the furnace on to minimize that error. This is a very simple control strategy, and there are many others. Well, let's analyze this simple one. Let's assume that the desired temperature is given by this dashed line right here and is a constant value. At first, when the system starts, let's assume that now the room temperature, which is the solid line here, is greater than the desired temperature. The error is positive. If the temperature is higher than the desired temperature, then the furnace stays off. And the output of the controller, the decision made by the thermostat, is to turn the furnace off. As the furnace stays off, the temperature will slowly decrease because of heat losses. Once the temperature now is below the desired temperature, the furnace turns on. The furnace turns on, provides heat to the house. The temperature now starts to increase again. And once it exceeds the desired temperature, the furnace turns off. And this process repeats on and on so that the room temperature oscillates around the desired temperature. Now let's look at the effect of disturbances. Let's assume that the outside temperature changes suddenly. Here we have the initial temperature, and now let's assume that it decreases all of a sudden. What happens? Well, now the relation between the input and the output changes. Now the duration the furnace needs to stay on in order to change the temperature by a certain amount changes. And that change is not known in the model. But because you're using a closed loop system, this will be accounted for in the controller. The result is given here. We see that because we have a closed loop system, the controller will automatically adjust for those disturbances and compensate for the heat loss. Now the furnace stays on for a longer period of time and it stays off for a smaller period of time. And this is a very good example that shows how a closed loop system can account for disturbances that cannot be modeled, which makes an open loop control strategy inefficient. Now let's look at another example. In this example, a controller is to be designed to regulate the speed of a car. The car is the plant or the process we want to control. The output of the process is the speed, and the input is the throttle angle. The throttle angle is given to the actuator, which is the engine. The engine delivers power to the car and the speed of the car changes. As we discussed before, the first step to design a control system is to understand the system we want to control. Here, we need a relation between the throttle angle and the speed. This relation would consider the dynamics of the engine, the dynamics of the car, mass, inertia, friction, etc. For simplicity, let's neglect all dynamics and let's simply assume that for a 1 degree change in the throttle angle, the speed changes by 10 kilometers an hour. That's the model of the car. This model only works if there are no external disturbances. We remember that we cannot account for disturbances in the model. What are the disturbances in this system? There are many disturbances, but for simplicity, let's only take one. Let's consider the road grade. Our relation between the throttle angle and the speed will only hold when the road grade is 0. If the car is going up on a hill, we have to press on the throttle more to make the speed change by the same amount. If the car is going downhill, then one needs to press less on the throttle to make the speed change by a certain amount. This relation of 1 degree, 10 kilometers an hour doesn't hold anymore. Now let's take this relation and consider that this relation is all we know about the car. And let's see if you can effectively create an open or closed loop control system to regulate the speed of the car in this condition. Let's also add this disturbance. That now let's assume that for every % change in the road grade, the speed of the car changes by 5 kilometers an hour. So if you go up on a hill, for every degree, the speed of the car will change by 5 kilometers an hour, and if you go down, the speed will increase by 5 kilometers an hour. Let's try to first develop a open loop control strategy using the model we have, and then let's move on to a closed loop control and compare them. Now, let me warn you that this analysis that will follow will be a bit complicated. The objective here is not for you to understand every single calculation that will follow, but just to focus on the big picture. What a closed loop control is and what it does, and what an open loop control is and how it is implemented. The analysis again will get a bit complicated, but it's not time to worry about the analysis. We'll break that down into smaller pieces and go over them over the following lectures. Let's once again focus on the big picture of what a closed loop control represents and why it's better than open loop control. To that, let's move to the light board. In this particular example, we are dealing with speed control of a car. And you have some information about the car. We know that when you press the throttle by a certain amount, the speed changes by a certain amount. And that proportionality constant here in this example is 10. By each degree that you press on the throttle, the speed changes by 10 kilometers an hour. If you call the output speed that is a result of the throttle angle y1, we can write that y1 is 10 times the throttle angle. Let's call the throttle angle u. So the speed I1 that results from the action that we give to the car, which is pressing on the throttle by 1 degree, is given by 10 times the amount we press on the throttle. This is all the information we know about the car. So now we can represent this expression as the input to our system, which is u, the throttle angle. If you take the throttle angle, multiply that by 10, we get in the output y1, which is the speed as a result of the throttle angle. This is the car model. This is all we know about the car, and this is all what it can control. Now, there are other elements acting on the car that are not part of our model. For instance, there is a road grade that will affect the speed. There is air drag in the front of the car that also slows down the car. There is friction between the wheels and the road. All those elements are external to the car, are disturbances to the system that we cannot account for. The only thing in this example that we know about the car is that by each degree that we press on the throttle, the speed changes by 10 kilometers an hour. Now let's complement this with the effect of the road slope. We know that the speed of the car is also affected by the road slope and will change depending on the grade of the road. By every degree, the information that we have is that the speed changes by 5 kilometers an hour. Let's call the effect of the grade slope on the speed y2. This is the speed that results from the slope. And we know that for every degree, the speed changes by 5. Let's call the slope w. W is the slope times 5 gives the effect of the speed to the car. What is the final speed? The final speed of the car is a combination of these two. The final speed is the effect of the throttle angle minus the effect of the grade slope. I'm assuming here that is negative. If the slope is positive, the car goes up, and you expect the speed to decrease, hence this negative sign. Now let's add this to our representation here. We need to now add the effect of the slope. This is a function. This is times 5, and this is w, the road slope. Here we have y2. y2 equals to 5 times w. This is what you have there. And here in the output of this that represents a sum, we have y, that is y2 minus y1. And this is now the speed of the car. Now that we have a good understanding of how the car responds to a throttle angle command, we can go ahead and create a controller. The controller will make sure that the car goes at the desired speed. Let's call that a desired speed R. If you want now the car to go at a speed r, what is the value of the throttle angle that we need to apply? To do that, now we need an understanding of the car dynamics. And the only information that we have about the car is this part of the block diagram. It's only the relation between the speed and the throttle angle. Remember that this portion here, we don't know about it. This is an external element acting on the car that you cannot account for in the controller. This is the road slope. All we know about the car is the relation between the throttle angle and the speed. But the final speed depends on other elements that I'm adding here just to exemplify how this controller will work or not, but we have no information in the controller about the road condition. All we know is this part here. Now we know that when you press on the throttle by 1 degree, the speed changes by 10. So if you want to go at 10 kilometers an hour, we should press by 1 degree. If you want to go at 20 kilometers an hour, then you press on the throttle by 2 degrees, which means that the relation now between the desired speed and the throttle angle is simply the desired speed divided by 10. It is the inverse of this gain here. If you want to go at 10 kilometers an hour, R is 10. 10 divided by 10 is 1. We give a throttle angle to the car of 1 degree. This is the controller. This gives the relation between the desired speed and the command that we give to the car. We can now expand this to include our control strategy. R now becomes the input, the desired speed. We divide R by 10. This becomes U, the throttle angle. This is the logic that we implemented. This is part of the controller. And this is now given to the car. It's given to the plant. So U times 10 gives Y1. And here we have again the effect of the road disturbance. This is times 10. And the output here is the final speed of the car. Once again, 3 components. This is the car model. This is what we know about the car. This is the controller that we developed based on the information we had about the car. And this is the external elements. These are the external elements acting on the car that are not known in the controller. They are not known in the car dynamics. Now let's see what we have here. We have created another expression between U and R, between the desired speed and the throttle angle. We can now replace this expression in the one that we derived before. U is R over 10. So Y becomes 10 times R over 10 minus 5W. So Y is R minus 5W. According to our controller, a very simple controller here, this is the speed. Now let's assume, for instance, that we want to go at 10 kilometers an hour. So R is 10. When the road slope is 0. When the road slope is 0, our commanded speed is 10. We give 10 to R. 5 times W is 0. Y, which is the actual speed, is 10. So this works. As long as we have no slope, as long as there is no slope, no grade in the road, our controller works. We want the car to go at 10 and ends up going at 10. Now let's assume that we have a 1 degree slope. We want to go at 10 kilometers an hour. So we give R a value of 10. And now there is a 1 degree slope, minus 5. The actual car speed is 5 kilometers an hour. So our controller does not work if there is any external element acting on the car. This is the so-called open loop control strategy, where we need a solid understanding of the plant that we want to control and all elements acting on that plant must be accounted for. Notice that here, the only information we had was this part here, only the relation between throttle angle and speed. Other external disturbances acting on the car were not accounted for because we don't have information about it. It's just added here as an example. Notice that the controller is only based on the car model, not based on the disturbances. We cannot account for all disturbances acting on the car. This strategy works assuming that the model is perfect, assuming that the model accounts for all disturbances and everything acting on the car. As soon as you have anything external to the model, our open loop control strategy fails. And now we need to consider the main idea in control systems, the so-called closed loop control. Now let's rethink this example using a closed loop control scheme. The main idea in control systems is to use the so-called error-based control. We are going to now measure the output speed of the car and take corrective actions based on the difference between the desired and the actual speed. The idea is very simple. Let's again give the car a desired speed R. And let's measure the difference between R and Y, the desired and the actual speed. So let's take a measurement of the actual speed using a speedometer or some sort of speed sensor. And now let's compare them. And here we created an error function. I'm going to call that epsilon. Epsilon is the error between the desired and the actual speed. Now here comes the main idea in control systems. Our control action now needs to become a function of this error, not a function of the speed itself, not a function of the desired speed only, but a function of the difference between them. And this will make a lot of sense. If you are driving and you are far from your desired speed, you press on the throttle by a certain amount. If you are very close to the speed you want, that amount will change. You are driving based on the error between the desired and the actual speed. You are taking corrective actions. You're applying a control action to the car based on how far you are from the desired speed. Not your current speed, but how far you are from where you want to be. Now that we have this error function, let's create here a controller that in this case will be a simple proportional controller. We're going to make the throttle angle proportional to the difference between the desired and the actual speed of the car. What is this value here? What is this proportionality constant between epsilon and u? There are many answers to that question. For now, let's put an arbitrary number here and let's see what happens. Now let's assume that I'm a very conservative driver and this proportionality constant between the error and the throttle angle is 10. This means that if I'm 1 kilometer an hour away from the desired speed, which means that the error here is 1, I'm going to press on the throttle by 10 degrees. Well, that doesn't sound very conservative anymore. It's a pretty aggressive controller, in fact. But let's keep that as it is. So for every kilometer an hour, we'll press on the throttle by 10 degrees. Now let's see how this system now reaches the desired speed. We have an expression for y here that we calculated before. Y was 10 times u minus 5w. And now we have a relation between y, r, and u. We know that epsilon is r minus y. And we know that u is 10 times the error epsilon. So we can now combine these two equations and write the control action or the throttle angle is simply 10 times the desired minus the actual speed. Now let's take this expression here and replace that on the same expression that we had before, that it gives the output speed of the car, accounting for when the road slope is modeled. That it gives y equals to 10 times u 10 times u is here, 10 times 10 r minus y minus 5w. Here we have y equals to 100 r minus 100 y minus 5w. Now moving 100 to this side of the equation, we get 101 y equals to 100 r minus 5w. And now we can finally find an expression for the final speed of the car. Let's write it up here. Now the actual speed based on this new control strategy that we created is y equals to 100r over 101 minus 5 over 101 times w. This is now the final speed of the car. Let's consider the same scenario that we had in the so-called open loop control that we considered first. In that scenario, our desired speed was 10 and the road slope was 1. And we saw that if you use our open loop control strategy, the result was 5 kilometers an hour. That's an error of 50%. If you now replace these values into these new expressions that we created here, the value of y, the actual speed of the car, will be 9.85 kilometers an hour. In the open loop control strategy, this was 5 kilometers an hour, was half of the speed we wanted. Now with this new scheme, our speed is 9.85 kilometers an hour, very close to the desired speed. There is still an error there, but it's much better than what we had before. What is happening here? Our controller now is taking continuous measurements of the speed, calculating the error, and slowly adjusting the speed so that the car will reach or approach a desired speed. Because we are now measuring the actual speed in the output, we no longer rely on a perfectly accurate model of the car dynamics and all disturbances acting on the car. Our actions are functions of the error between the desired and the current state of the car. So now we can allow for these disturbances to exist. And this is the main idea in control systems, is to watch the output we want to control and take actions based on the error between the desired and the current output. Now this is a very simplified example. We forgot one major thing here is the dynamics of the car. The dynamics of the car in this model would account for the car mass, inertia, acceleration, motor dynamics, and so on, so that we have a better understanding on how the car responds to a certain command. Now let's consider that scenario where you have inertia here. If you have inertia and you accelerate too much, the car will eventually exceed the speed. And when the car exceeds the speed, now the error here will flip, will become negative because you are now beyond the speed we want to be. So you're going to release the throttle angle. If this gain now becomes too high, this controller will press on the throttle all the way and release the throttle. As the car speeds up, exceeds the speed, release the throttle. Now the speed is decreasing, is lower than the desired speed, so the error becomes positive. We press on the throttle again all the way, and the car starts to speed up, and you keep pressing and releasing the throttle because our control gain here is too high. We cannot see it right here because the dynamics of the car are missing. This example at this point probably doesn't make much sense, I have to admit. This has a lot of concepts that are going to cover throughout 22 lectures. So if you don't understand this concept very well right now, don't worry about it. We are going to now break down this problem into small parts and address one of them at a time. We are going to start here with modeling of mechanical and electrical systems. Then you're going to move on to the control systems part, where you're going to see what is the actual function you need to put here to make the car work. How do we minimize this error? We are not very close to we are very close to the desired speed, but you're not quite there. How can you fix this? How can you minimize that error? This block diagram representation is another example they're going to cover in one entire lecture. So all these concepts now will be broken down into small parts, and you're going to address them one by one. This is just an idea to give an example of what a closed loop control system is, what the main idea in control system is, but the specifics of it, once again, we're going to detail that in the upcoming lectures. In this course, we are going to deal with linear systems. Thus, it is important to define what a linear system is. A linear system needs to satisfy the properties of superposition and homogeneity. Let's consider superposition first. If we apply an input x1 to a system, one obtains output y1. If an input x2 is given, consider that the output now is y2. Superposition requires that if now x1 plus x2 is applied to the system, to the same system, the output is a superposition of the previous outputs, that is y1 plus y2. If this condition is respected, the principle of superposition holds. Now let's look at a homogeneity. Now consider that the same input x1 is given to the system and we obtain a output y1. If now alpha I x1 is applied to the system where alpha is a constant, a scaled version of the same input, the output needs to be alpha times y1. If this happens, then the condition of homogeneity is also respected, and when superposition and homogeneity are met, then the system is said to be linear. Are these systems linear? Let's take the first one. If we apply now x1, the output of the system will be mx1. If we apply x2, the output of the system is mx2. If we now apply x1 plus x2, the output of the system will be m times x1 plus m times x2, which is m times x1 plus x2. The principle of superposition holds. If we now again to the same system give an input x1, we will obtain an output mx1. If you give now alpha x1, the output will be m alpha x1. The second condition also holds, and the first system is indeed linear. Is the second system linear? Clearly it's not, because of the square in the output. If y equals to x squared, for x1 the output is x1 squared, the output when x2 is applied is x2 squared, and the output for x1 plus x2 is x1 plus x2 squared, which is different from x1 squared plus x2 squared. Is the third system linear? At a first glance, it appears to be linear. Let's put some numerical values there to confirm it. Let's assume that m equals to 2 and b equals to 1. So the output is 2x plus 1. If you give an input x1 of 10, the output y1 is 10 times 2 plus 1, 21. If you now give an input of 5, which is half of x1, the output should be half of y1. Is it? Well, if x2 is 5, the output is 2 times 5 plus 1. y2 is 11. And y2 is not half of y1, even though x2 is half of x1. The system is not linear. A main limitation of control systems theory is that everything needs to be linear, but most systems are in fact not linear. Let's consider this MECE spring system, where the stiffness of that spring, or the force applied by that spring, depends on the square of its displacement. Something similar to the system we saw here. This is not a linear system. If you now plot the force developed in the spring and the displacement of the spring, we have a quadratic function. This is not a linear system. How can we now make an approximation? Now let's assume that we are operating around a specific point y prime, and assuming that we are only operating around y prime, we may be able to create a local model that is almost linear. Around that point, we could assume that the force and the displacement have a linear relationship, and now linearize the model around that operating point. We see that here around y prime, we could assume that f and y are simply proportional to each other, and this would indeed give a linear model. But that linear model only holds around this operating point. Here is another example. Let's consider this pendulum. The pendulum has a bob with mass m, a length L. Let's call theta the angle of the pendulum with respect to the vertical axis, and tau the torque applied at that pivot point. The relation between the angular position of the pendulum and the torque applied at the pivot is given in this equation. We see that because we have a sine function here, this will make the system nonlinear. Can we now linearize the system? Let's, for instance, assume that our operating point is around 0. So theta is very small. It tends to 0. And the pendulum only operates around a small angle that is around 0. Considering our operating point and assuming that theta is very close to 0, we could approximate sine of theta as theta. And this again only holds when theta is close to 0. This means that the first equation in green can now be simplified to mgl times theta. This now is a linear model, but it only works provided that theta is close to 0. If you plot the first equation, we should get a sine wave that follows this trend. If we now plot our linearized version of that model, that will give a straight line, and you see that this only holds around 0. As the angle now starts to increase or decrease, you see that there is a significant discrepancy between the actual model and the local linear approximation. So the local linear approximation, the red line, only holds at a specific operating point. In this case, theta is approximately 0. Now let's go back to the light board and do 2 exercises to help clarify the concepts of feedback control. Each exercise will be discussed in a separate video.